some of the work that he presented in the first Lahti Lake Symposium 3 years ago. So, Mark, I hope that you can hear me over there in California.
I can, and good morning from California. So I will be talking about hypolimnetic oxygenation in Hodges Reservoir, California, and thank you again for inviting me to present at this second Lahti Lakes conference. Some acknowledgements here, my graduate students, staff at the City of San Diego, and also the California Water Board. Of course, we don't do this work all by ourselves. So a bit of project background and objectives. The project driver here is the City of San Diego is working to enhance and diversify potable water supply in water-limited Southern California, where new water supplies can cost on the order of $3 per cubic meter. The study site, Hodges Reservoir, is a hypereutrophic reservoir with poor water quality, and this limits its potential for use as water supply. Starting in 2020, a hypolimnetic oxygenation system was installed with the aim of improving water quality and enhancing water supply. I might add, too, that a number of watershed management efforts are going on as well to try to control external nutrient loading. But this is a Mediterranean reservoir, no inflow during the summer, and internal loading controls production during that time. The objective of the study really, well, there's a number of ongoing studies that are assessing how hypolimnetic oxygenation affects chemical cycling and water quality, including nutrients such as ammonium phosphate, redox-sensitive metals that can affect water treatment, such as iron and manganese, and then ecological toxins such as methyl mercury, a particular research interest of mine, algal-related toxins, and also the formation of disinfection byproducts that are associated with dissolved organic carbon and nitrogen. So here's a bathymetric map of the reservoir. You can see it's long and sinuous. It's got the San Dieguito River coming in the east, and it's a big watershed, a lot of agricultural and urban development, so a lot of historical external loading to this system. There's some unique things to notice here. So the dam is down here on the west. We have Station A and Station B, monitoring stations we'll allude to when we look at some of the data. There's other stations upstream as well. The reservoir generally does not fill as large as you're seeing the footprint here. It really fills to this first kind of depth line. But there's some interesting onshore facilities to keep in mind. We've got a hypolimnetic oxygenation system down here by the dam. That includes an onshore oxygen storage tank and a submerged cone. There's also this interesting pump storage system up near Station B, where there's actually a reservoir of higher elevation near Hodges, and they pump water up during the night and then send it down during the afternoon to produce electricity at peak times. And this is a big money maker for the city and the other entity that operates this upper reservoir. So, real low Secchi depth here, very productive reservoir, pretty shallow mean depths, right? So this is not an especially deep reservoir, and during the summer, you can imagine the anoxia in the bottom combined with the bathymetry leads to pretty elevated internal nutrient loading and high productivity all summer. Here's some pictures. You can see the Mediterranean flavor of the system and a lot of development in the watershed. This study kind of, I got the chance to present on this in Lahti Lakes 1 and was involved in the special edition that came out where we talked about methyl mercury cycling and also cycling of other redox-sensitive compounds. This was kind of the study leading up to and informing the oxygenation system installation. As part of that first study, we did some chamber incubations, pretty comprehensive effort at understanding the fluxes of compounds under oxic versus anoxic conditions. And kind of the take-home message was oxygenation of the sediment-water interface did cause or suppress release of a lot of the nutrient loading and metals loading out of the sediments. In the case of ammonia, you can see it went from generally kind of a negative flux after the system was oxygenated for a while to a pretty classic elevated ammonia flux of around 100 milligrams per meter squared per day. So we're trying to get at control of internal nutrient loading with oxygen addition. Also here, just to set kind of the picture, are some profiles, heat maps for the system from 2017. So we get this classic thermal stratification in the spring, and then the descending thermocline, and just this enormous oxygen demand. As soon as the system just slightly stratifies, you can see we get hypolimnetic anoxia. And even when the system destratifies later on, the water column has low oxygen and never really reoxygenates. So I also measured sediment oxygen demand in the system. It had the highest sediment oxygen demand of any system I've worked on. So it's really a big oxygen monster. And then we see these classic patterns of bottom water accumulation. These plots are depth versus time, the classic kind of isotherm approach. And you can see phosphate accumulates at up to 5 or 6 milligrams per liter. That's ammonia. Phosphate's down here at a couple milligrams per liter. Manganese, and then a special unique observation was this methyl mercury patterns that seem to have a hot spot early on in the season under moderate reduced conditions. I should add too, this is a sulfate-rich reservoir, so we get a lot of sulfate reduction in the system, and that's generally coupled with methyl mercury production. Sulfate-reducing bacteria can produce methyl mercury. So on to the current situation. So we've got this oxygenation project in Hodges. It's to improve the treatability of the water for potable use. The idea here is try to repress internal nutrient and metals loading. The system included an onshore liquid oxygen storage tank, a submerged cone near the dam. The capacity of the system was 6 tons per day. So once we use the liquid oxygen is converted to gaseous oxygen, then put into the cone. And so these systems are very small, relatively speaking, but put in a lot of oxygen. The cost was about $5 million, and the annual cost to supply this oxygen over the years around $250,000. Those may sound like big numbers, but the value of the water in the reservoirs is around $20 million, real back of the envelope calculation. But this is free water to the city, and to go out and get new water costs a lot of money, and it's free water that's currently not being used because of the degraded water quality in the reservoir. So unfortunately, I have 3 years of pre-oxygenation data set, but then the UC Merced monitoring contract was terminated with the COVID outbreak. The city, like a lot of utilities, really pulled in and focused on mission critical work. And so we lost our contract right in March when we were just nailing it down when the COVID outbreak happened. So we're in this kind of interesting situation of 3 years of comprehensive preliminary data, and then the city took on some water quality monitoring after that, but not in the same way or with the same frequency or coverage that I had done before. So here's some pictures of the oxygenation system. We've got this liquid oxygen storage tank and evaporator on shore. This is technically from Comanche Reservoir, but you can imagine it's a very similar footprint and very modest footprint as well. You see the fence here for scale. And down on the bottom of the reservoir, we've got this submerged cone. You can see the cone being launched on the barge. And you have a submerged pump that sucks the water into the top of the cone. You inject the gas into the top of the cone, and you have a countercurrent contact chamber, and out comes your highly oxygenated water with 50 milligrams per liter oxygen or more. A big part of the cost was unexpected geotechnical issues at the site. There turned out to be more soft sediment than they expected. So if there was a little more information earlier on about the geotechnical situation, the cost would have been lower. But you get the idea, the oxygenation systems down by the dam. We'll be now looking at data from Station B. This was one of the issues with the city's monitoring. They didn't want to go all the way down to Station A to collect samples. Station B is by the boat dock. So we're looking at Station B, water quality, with my data for 3 years before, and then some of the city's data. And so you can imagine the oxygen is being injected here. Natural advection is presumably moving the oxygen around the system, as of course it's being consumed too. So we will look at data from Station B, keeping in mind it's about I'd say a half a kilometer away from where the oxygen injection was. So I'll show you now some series of water quality data with time. And oops, let me back up here. So we're kind of missing our axis here, but this left figure is ammonia, and it's going up to the same scale as the nitrate, 5 milligrams per liter nitrogen. So you can see in the previous years, and this is bottom water, it's an average of samples collected every 3 meters down the water column, this classic accumulation of ammonia in the bottom. And then post-oxygenation, this is samples collected by the city, which consist of a upper hypolimnion and deep water sample. We're not appearing to see this ammonia peak. And there's also some interesting patterns within the nitrate concentration, average concentration in the hypolimnion. You can imagine there wasn't any when we went out there during the summer because of the reduced conditions in the system. And we didn't measure what happened in the winter. But what happens in the winter is this ammonia gets nitrified and you get this nitrate peak, and that's captured between 2019 and 2020. And then we see some interesting dynamics here with the nitrate. It looks to me as if they started the oxygenation, the nitrate was going down. They started the oxygenation system, and that may have alleviated some of the nitrate demand as the plume of oxygen arrived at Station B, and maybe enhanced ammonification, and those combined caused the nitrate to go back up and then back down, as perhaps the oxygen system was still delivering some oxygen, but there was nitrate demand as well. And I think in 2020, they may have not really turned on the oxygenation system as high as they could have. Of course, I don't have the DO profiles yet. But anyway, interesting patterns here. But in the end, it looks like there's less total inorganic nitrogen down in the bottom waters. With respect to the phosphorus, we can see, I'm just keeping an eye on time here if I can. We can see the phosphorus in the surface water and the bottom water. It looks like the phosphorus levels in the surface water are relatively low compared to previous years. Again, this is the same 1 milligram per liter scale as on the right figure. In the bottom, you can see this classic hypolimnetic accumulation of phosphorus due to mineralization and probably and iron oxide reductive dissolution, and that seems to be muted here post oxygenation. And finally, we got total manganese and total iron. Again, the scale here is 1,000. And we see this classic manganese accumulation is muted post-oxygenation. That's a very good sign that the system is not experiencing low redox conditions. And then iron seems to increase a bit. Now, again, I didn't sample in the winter. These winter iron could be associated with storm flows, but even then, some of the iron during the stratified period seems to be higher. And our thinking there is we're alleviated of the sulfide sink for reduced iron through the precipitation of iron sulfides. Now that we're oxygenated, we're getting less or no sulfide, and that is alleviating the sink for what little iron may be coming out of the sediments. Methylmercury, we're not sure. We saw some interesting patterns of methylmercury accumulation in the bottom waters. Of course, methylmercury bioaccumulates in aquatic ecosystems. We're starting up some monitoring this year to see if oxygenation, how it affects mercury cycling. One concern is this 2017 versus 2018 interesting case studies. 2018, very dry year, very reduced conditions in the reservoir early on, and less methylmercury production due to repression by sulfide. It was 2017 where there were these moderate kind of reduced conditions down in the bottom all season that had the high methylmercury production. So the methylmercury seems to be produced under modest redox conditions. And so we've now added oxygen to the bottom of the reservoir. It could repress methylmercury, but if we get into the sweet zone of modest reduced conditions, it could enhance it. So we'll see what the response is. So conclusions, hypereutrophic Hodges Reservoir exhibits high rates of internal nutrient and metals loading that stimulates algal production and degrades water quality. Experimental chamber work showed the maintenance of an oxidized sediment-water interface suppressed nutrient and metal release from the sediments. And then preliminary data seems to indicate the system is working. Relatively low ammonia and total inorganic N concentrations, relatively low total phosphorus in surface and bottom waters. Of course, in the surface, the TP could kind of be an analog for phytoplankton. The city's not doing chlorophyll A samples. And then relatively low manganese, but higher iron concentrations. As far as the mercury goes, we're going to continue monitoring that on our own expense this year and try to get funding for 2022. And we hope to report the results at the Lahti Lakes 3. So thank you very much, Kitos. And again, good morning from California. Thank you.
Thank you very much, Mark, for this great talk. And yes, so Mark is already advertising Lahti Lakes 3, and we hope to announce also at the end of the symposium on Wednesday that we will indeed intend to host such a meeting in 3 years' time. So thanks for this plug already. And yes, it was interesting to hear you talk about some of the problems that you've had, for example, financing your sampling and analytical programs last year. And of course, Raul also mentioned that his sampling was severely affected last year. And I guess many of the participants have had similar stories of the difficulties that we've all had to continue the work that we do during the last year. So yeah, we sympathize with your situation. Pulled together the data that was available, and this was a very interesting talk. So just quickly, because we have only a couple of minutes before we move to the online chat, but 3 questions have come in already. So Mark McCarthy is on the ball again, and he's complimenting the interesting talk and asking you if there's an explanation for the lower ammonium and generally high nitrate seeming to start prior to the oxygenation. Was that a real effect, or is that just Mark seeing things that were not there?
So I'm not exactly sure what you're alluding to, and we can start chat further, but it might have been we see an increase in nitrate in the water column in the winter after the ammonia accumulates during the previous summer, mixes and gets oxidized to nitrate. So we do tend to see this peak of nitrate out there in the spring, and it's kind of an interesting phenomenon because nitrate's a good oxidant, right? So it probably is helpful and buffers how quickly the system goes anoxic the following summer. But there is this kind of mystery bump of nitrate in the last winter after the oxygenation year 2020 that we're not sure about.
Okay, a couple more questions. Firstly from Gertrude, and she's asking, did you find higher iron in other aeration and oxygenation treatments?
Yeah, iron's always kind of one of the hardest compounds to track and understand cycling-wise when we try to understand the impacts of oxygenation and look at water quality data sets before and after. Honestly, a lot of these systems go in and folks are not so focused on the metals. So I can't say I've documented or seen where iron has increased post-oxygenation. Keep in mind, Hodges is a pretty interesting system. It's very sulfate rich, so it's kind of unique in that sense and unique in the amount of sulfide it accumulates and the resulting potential for iron sulfide precipitation.
It was a very interesting observation how you saw that the iron concentrations were increasing in the absence of an increase in the manganese concentrations. And this caught my eye in the sense that I think also in your paper in the special issue you were highlighting the relative kinetics of the oxidation of iron and manganese, that iron is typically being oxidized more rapidly, so you're more likely to see an accumulation of manganese. Whereas in this case, you're seeing an accumulation of iron, whereas the manganese seems to be well trapped by the oxygen. So that was for me also quite an interesting observation. Do you have a response to that quickly?
I guess some of those peaks in iron were during the winter, and because we know how manganese and iron cycle, my thinking is it might be in inflow and external loading coming in during the winter inflow.
And just quickly, maybe I can ask one of the two remaining questions from the chat here. So Kalevi Salonen is asking, maybe the pump station could be used for oxygenation by leading returning water to the lake bottom. Do you have any comment to this idea?
So I'm not sure I quite understand the question, but the intake is there on the bottom and the water goes out at the bottom as well. So you have the submerged cone, it takes in bottom water, it oxygenates it to very high concentrations and then discharges at the bottom as well. So it's a point input of oxygen. The oxygen is stored up on the shore, turned to gas, but ultimately injected down in the bottom of the reservoir. And partly we want to do that because we get the hydrostatic pressure and that increases the amount of oxygen the water can hold.
Okay, thank you very much, Mark Beutel. And indeed, thanks to all the presenters of today's 3 sessions. We're very grateful for your contributions. So all that is remaining for today is that we will now move to the online chat one more time to continue the discussion about the presentations in this final session on physical methods. And then at the end of the chat, we will return briefly to the studio just to sum up quickly the contents of the day's presentations and what we can take home. But yes, thank you already from me for the participation and all the presentations. And let's move to the chat room.